In this video, I'd like to talk about the notion of where the Fourier series converges. So for Taylor series, we said that those converge as long as the x value is within the interval of convergence, but there's no notion of an interval of convergence for these global approximations that we get from Fourier series. Instead, there is a theorem that is called the Fourier Convergence Theorem that is going to tell us that pretty much wherever f of x is known to be continuous, then the Fourier series converges to the value of the function there. So that would tell us how to find the sum of the series. And the Fourier series also converges at x values where f of x has a discontinuity, except that it doesn't converge to the value of the function, but rather in this notation I've written here, if it has a discontinuity at a, then it converges to 1/2 f of a plus f of a minus. So what do I mean by that? Just as a little sketch here, suppose that we have this function that has a discontinuity at a, and we see that it has a jump here that on one side it is evaluating to, or it's approaching 1, and on the other it's approaching 3. So in this illustration, 3 would represent f of a plus, because that's what's happening to the right of a, and positive 1 would represent f of a minus. And so if I had to think about where the Fourier series would converge, that would be the average of these two values. So 1/2 1 plus 3 would give me 2. So the Fourier series would actually converge to the value of 2 here. So what we'll look at are a few applications of this. So one of the applications is that this would allow us to graph the Fourier series. And if this is asking me here to graph the Fourier series for this function, as you can imagine, the Fourier series itself would be a very complicated sum. And so if I looked at the Fourier series, it would not in any way be easy for me to think about what the graph of that would look like. What I'm doing instead is thinking about the graph of f and just paying attention to where its discontinuities are. So for comparison, I'll graph f of x. So this function is going to look like the following. So we're told that from minus pi to pi, this is going to go from -1 to +1 up here. And it's open on the right endpoints and closed on the left. And part of what I have to be able to do here is what we call a periodic extension of this. So this would then also extend like this if I went from pi to 2 pi. And if I looked at -2 pi to pi, this would look like this here. So in my graph here, these are scaling of my y-axis, and this would continue. So this is, importantly though, this is not the Fourier series. This is the graph of f of x. So using that, the Fourier series graph, sometimes I'll see a capital F of x used, but with the graph of f in front of me, what I want to look at is how I can adjust that to graph the Fourier series. So everywhere that that original function is continuous, essentially avoiding those endpoints, I'm going to graph the identical thing. So this and this, this here, and I guess this would be a little bit longer, this here. And what is different is I'm going to leave all of the edges here open. So that's one big difference. And that's because the Fourier series does converge at those points, so I don't want to leave them open entirely. But where it converges is to the average value of, in this instance, -1 and 1. So the average value would be 0. So every time I have a jump from one piece to the other, or a discontinuity, the Fourier series evaluates to the middle point of that jump. So notice the importance of how these are very similar, but there's a difference at the discontinuities. So that would be my Fourier series. As another example, look at what I have here. Same thing, I would start off to graph f of x. So if I were to graph f of x, this is one we've actually found the Fourier series for. That looks like this from -pi to pi. So this would be 1. And by thinking about what would happen if I extend this past this one period, it would just repeat itself. So this would be to 3 pi, and this would be out to minus 3 pi. And again, the way I've written this, there's not an obvious x value to extend this out to. But this is the graph of f of x. And so if I want to now think about the graph of the Fourier series, again, I look at the graph of f of x and I don't think about the structure of the Fourier series. So like I said before, I take the graph that I have for f of x, and everywhere that it's continuous, I draw the same exact thing. But notice what happens here is, in fact, the graph that I drew above, this f of x, that's going to be continuous everywhere. So if the original 2 pi periodic function is everywhere continuous, then the graph of the Fourier series would be identical to that. So we can see the kind of distinction here between, we had one where we had discontinuities, the graphs were different, and when we had continuity everywhere, the two graphs were the same. And it turns out that this Fourier convergence theorem has another very nice consequence, that it allows us to find the sum of series that we, previous to this, did not know how to sum. So in a previous example, we saw that the 2 pi periodic function f of x, whoops, where we know that f of x is minus x from minus pi to 0, positive x from 0 to pi. So I'll point out this is an example here, but I actually mean a previous example in a different video. We actually found the Fourier series for this. So we saw that this had Fourier series given by pi over 2 plus the sum from k equals 1 to infinity of -4 over pi times the quantity 2k minus 1 squared times cosine of 2k minus 1 times x. So we went through the work of finding that before, but given that we have that relationship, let's now use this to find the sum of k equals 1 to infinity of 1 over 2k minus 1 squared. So the way to approach this here is to think about the fact that I know that that Fourier series above converges everywhere where x is, where f of x is continuous. And in particular, we saw in the graph up here that that's actually for all x. So from the Fourier convergence theorem, we know that f of x is equal to this sum. And in this case, it's 2k minus 1 squared, cosine 2k minus 1 times x. So when f of x is continuous, and here that's for all x. And I mean, like, if we had a different example, it might not be for all x, but for us, we know that's everywhere. So I now have this equation where I have an x, of course, on both sides, and inside of the function f, but also inside of my sum. So what we can do is plug in an appropriate value of x to both sides. And when I say to both sides, I mean in this equation here. So what do I mean by appropriate? Think about, we're looking at the summation that I have here, and I'm trying to think about how I could get the desired sum out of that. One glaring difference is that there's no cosine in the desired sum. So one thing to think about is I would like to plug in a value of x that would make that would make this easy to get rid of the cosine. So if I'm looking at cosine here, for instance, we know that cosine of 0 is 1. You could really use, you could use for that 2 pi, 4 pi. So there's not just one correct answer. Often I like to focus on, the interval around 0. So with these, you kind of want to play around with it and think about plugging in something that would make this look more like the series that we have there. So I'm writing here, try x equals 0. And that's because I'm thinking of the fact that cosine of 0 is 1. So what that means is that plugging that into the left-hand side of the green boxed equation, we get f of 0. And on the right-hand side, we already observed that the cosine term, because it's multiplied, vanishes. So times 1, and that's coming from cosine of 0. The thing to think of here is, what is f of 0? Well, we know that f of 0 is coming from this part. I could also think of my graph, but when when x is 0, we know that this function, the given function, evaluates to 0. So the next thing to think about is to use that. So this evaluates to 0. We have the pi over 2. And then the other thing I want to think of is I have this sum here, which has terms minus 4 over pi times the quantity 2k minus 1 squared. And the sum that I'm trying to evaluate doesn't have that minus 4 in the numerator, and it doesn't have the pi in the denominator. So with that in mind, I want to rewrite this as minus 4 over pi times the sum of 1 over 2k minus 1 squared. Again, keep in mind that we're allowed to do that because the minus 4 over pi is a constant multiple inside of the summation. So the advantage is now I see what I am trying to evaluate, right? This is the sum that we want to find. And we have an equation, so I can actually now manipulate this. So I can subtract pi over 2 and say that minus pi over 2 is equal to minus 4 over pi times the desired sum. And then finally, if I want to isolate that sum, we want to get rid of that multiplier of minus 4 over pi. So we're going to be able to say that the sum of 1 over 2k minus 1 quantity squared is equal to negative pi over 2 times pi over minus 4, so multiplying by the reciprocal, and we end up getting that the negatives cancel, and I get pi squared over 2 times 4, or 8. So this Fourier series allows us now to find the sum of certain series that we couldn't before, right? This isn't geometric, it's not telescoping, and it's also not related to one of our familiar Taylor series functions. So these are just a few applications that we get from this very powerful theorem, the Fourier Convergence Theorem, that also demonstrates why we think of these as global approximations in comparison to Taylor series, which we think of as more local approximations.